Hello, everyone, and welcome to the last chemistry lecture of the semester. So today we're going to be taking our knowledge of enthalpies and applying them to solutions. So one of the big things we need to make note is, enthalpies of formation are going to be treated slightly different when we're talking about reactions that involve electrolytes. And one of the reasons why is if I have an electrolytic solution, it doesn't just go from the liquid phase to the aqueous phase. It does something kind of special. It breaks apart into protons, it breaks apart into its constituent cations and anions. And when it does this, this cleaving of the bond, essentially, or ionization, has its own enthalpy involved. And this actually does kind of convolute our enthalpies of reaction. So commonly what we end up having to do is when we're dealing with systems that can essentially break apart in solution, we have to account for the fact that the cation and anion are going to be different. So for example, if we're looking at HCl, one of the things we have to do is we'll have to take, for our enthalpy of reaction, the enthalpy of the proton plus the enthalpy of the chloride ion, and then we'll subtract out our original reactant, which was HCl in the gas phase, which is the default form of HCl. So this enthalpy of reaction is typically referred to as an enthalpy of solvation, going from either a solid to an aqueous phase, or a gas to an aqueous phase, or a solid to an aqueous phase. And the enthalpies of formation for the original solid or gas phase species are usually known. So then all we have to really worry about is the enthalpy of formation for the ions. The unfortunate part is that both of these ionic species are often unknown. So if we were able to measure the enthalpy of solvation, we would still not have enough information because you need to have at least one of these species known. And by convention, what we do is we artificially set the enthalpy of formation for a proton to 0. So this is, again, just a common convention, but once that happens, everything else falls into place. Because if I know the enthalpy of formation for the proton, and I'm able to measure the enthalpy of solvation for this reaction, then I can figure out the enthalpy of formation for the other species, in this case, chloride. And you can do a very similar process for fluoride, bromide, and iodide. And then, because we will know the enthalpy, we can measure the enthalpy of solvation, and we can go ahead and look in a table of the enthalpy of formation for our gas phase HCl. Once you have the enthalpy of formation for chloride, then you can go ahead and use this along with, say, the enthalpy of solvation for sodium chloride to determine the enthalpy of solvation for sodium. And then once you know sodium, you can use this to determine almost anything else, because in between chloride and sodium, these are two of the more common species that ions that make strong electrolytes. So you can do a very similar process. As long as you know the enthalpy of formation of one of your ions, you can always determine the enthalpy of formation of the second one. And using this, we can generate a wide array of enthalpies of formation for a huge number of different ions. So there's a lot of things you can do. Sometimes you're going to want to determine the enthalpy of formation for an ion that isn't well known. This could be often the byproduct of an acid-base reaction, which produce a fair number of ionic species. And sometimes what we really care about is, well, what's going to be the enthalpy of solvation for a known species? So something like table salt. If I throw table salt into water, is this going to be an exothermic or an endothermic reaction? Well, if you're not sure, what you can do is simply take the enthalpies of formation for your ions and for the solid. Then it's a good old products minus reactants. So in this case, I can take my products, sodium and chloride, and then subtract out my reactants. If you're working with a more complicated species, make sure you take into account stoichiometry. In this case, we know the enthalpies of formation for sodium and chloride, so I'll add those together, and then I'll subtract out the sodium chloride. And when I do it, I find out that the enthalpy of solvation for sodium chloride is 3.8. Now, one of the cool parts about this is notice that this is a positive 3.8. It turns out the enthalpy of solvation for sodium chloride and some other common salts are actually endothermic. So this is a way that you can mildly cool down a fair number of aqueous solutions. Add a little salt, it'll get just a little bit cooler. Now, you may note this may not be a lot, And you can go ahead and figure out exactly how much this would cool down a liter of water based on what we know about calorimetry. So all these processes can really tie themselves together and illustrate some cool features of how reactions generate and consume heat and how we can use this to make predictions about our world. Thank you for a great semester and take care.